Let's pray. God, we thank you for the changing of seasons, both in our lives and in the world in general. And God, right now we want to lift up all of the people who are grieving in Las Vegas and in Nevada. And God, we thank you that not more were hurt. And God, we ask you just to bless and to comfort, God, those that are mourning. And God, for us today, God, we ask that you would open our minds so that we would understand what it is that we have to do with algebra, knowing that this is just a small part of what you're doing in our lives. And we thank you for it in Jesus' name. Amen. Amen. Okay. All right. Now, this lesson that we're going to work on today is one of a number of steps that in Algebra 1 you went through systems of equations. And in systems of equations in Algebra 1 you learned replacement and a few other steps. And when you got to elimination, you realized, hey, I can use elimination on all of them. And so the other ones, unless I see it and need it, I really don't have to use anymore because elimination works on all of them. Well, what we're going to find out today, and what I want to spend some time doing, is talking to you about something that works even better than elimination. Okay, so the first thing that I want to do, though, is to remind you of where we are. Okay. Now, your assignment coming up this week is in chapter 4. All right? We are going to finish chapter 3, and I'm going to give you a test for chapter 3 to take home and do. That's part of our regular planned assignments. And then when you get into chapter 4, you're going to do linear systems. Right, and this is all from the syllabus, so but I'm just showing you what it is. And then system solutions, right? And then finally, second order determinants. And this is what I'm going to talk to you about. Second order determinants is a way when you have two variables and two equations to be able to come up with the value of x and the value of y, which is where those two lines cross. Right, that's called the solution to that system. Right, how to get that anytime. If it's a whole number, then the value that you get will come out really nice because it'll turn out to be a whole number. If it's not a whole number, then you'll have a fraction. All right, and you should get used to fractions, improper fractions, simplified as far as you can. That means you take out your common factors. If you have a numerator or a denominator, that's a prime number. All right, and you should remember that from earlier. There was a reason for learning what prime numbers and what composite numbers were. And that was when you get into high school and you're doing fractions that are improper fractions. Once you have taken out all the common factors, you'll have a prime number on one side, and the other side is either going to be prime or composite, but unless it's in the prime number multiplication, a multiple of that prime number, then you can't simplify any farther. And those things are called relatively prime. If you have a 7 over 6, right, that's an improper fraction, 7 over 6. All right, is 7 a prime number? The answer is yes, because you can only break 7 down into 7 times 1. Now, 6 is a composite number, but related to 7, what they have in common is 1. And so you have 1 times 7 over 1 times 6, which is called relatively prime. Between those two numbers, you can't simplify any farther. If I had 7 and 14, I would have 7 over 1, right? 7 times 1 over 7 times 2. And in that case, the 7s would simplify out, and then I would have 1 over 2. And 1 over 2 is relatively prime. right? And that's what we used to call fully simplified, right? Okay, so when you have fractions in the determinants, when you have a fraction that is relatively prime, then you can stop, because the calculator will give you a decimal value if you need it, right? But the calculator doesn't know what two numbers to put in, right? It doesn't know the numerator, it doesn't know the denominator. Okay, so that's what we're going to work on. Okay, questions? Got you scared or confused? A little of both. A little bit of both. Okay. All right. So, all right. Now, this is something that I wrote several years ago for Algebra 1. And you don't have to take notes on this because you know this, but I'm going to sort of read it because this is the general place of where we're headed as we get into Chapter 4. It says, linear equations solved at the same time are called simultaneous equations or a system of equations. Now, those are vocabulary words. Sometimes you'll see simultaneous equations. All right, and so simultaneous means you're doing something at the same time. When you solve two linear equations at the same time, the only place where they are equal is where they cross. Okay, so that's what we're basically looking for. There are three possible situations, though. Either the linear equations have the same slope, or they have different slopes. All right, that's the first. If they have the same slope, then they're going to be parallel, and they're not going to cross. So the solution will be the null set. There will be no solution. Okay? All right? If the slopes are different, then they are called consistent and independent. If the slopes are different, then they're going to cross. And so the two vocabulary words that were part of Algebra 1 is that they're consistent and they are independent. Because they're independent, they're going to cross. Because one's going its one way, and the other's independent, it's going its way, and so the two of them are going to cross someplace. Okay? All right, they have only one solution. Okay? Now, their point of intersection is where the solution is. When the slopes are the same, the equations are consistent and dependent. When the lines are simplified. All right? Such equations lie atop one another. In other words, if you have an equation that's a multiple of another equation, right? For them to be, what is the word? For them to be consistent and dependent, the one is on top of the other. Okay? So, in that case, what is their solution? Their solution is all values of x. Right? Okay? Now, and there's an infinite number of solutions for that one. However, when the slopes are the same but the y-intercepts are different, then the equations are called inconsistent and there's no solution. Okay, so here's an example of what that's talking about. Okay, now, if we look at the slope, and what we talked about last week, in order to be able to get this in the slope form, -3 divided by 5 is the slope. Remember that? Okay. The slope for this one is -3 divided by 2. Are the slopes different? -3 divided by 5, -3 divided by 2. The slopes are different, so they're going to cross at one place. There's one solution. Okay? Now, this one. I have a slope of -2 over 4, which is -1/2. And here I have -4 over 8, which is -1/2. Okay? The slopes are the same, and if you'll notice, this multiplied by 2 will give me the same slope, but 2 times 10 is not 40, so those lines are not on top of each other, they are parallel and separated. And so there is no solution. Right? Now over here we have a situation where again I have -2 divided by -1, which is +2, -6 divided by -3, which is +2. So I have a slope that's the same, but if you'll notice, 3 times 2 is 6, negative 1 times 3 is negative 3, and 3 times 4 is 12. Those are the same lines. One is on top of each other because this is a multiple of that one, and so therefore there's an infinite number of solutions. All right, those are the three situations that you're going to have when you have systems of equations. Okay? All right, now that's a review, so now we're going to look at some actual work. All right, here's the two equations. Now, if I wanted to eliminate the x's, what I see is I need to take this equation and multiply it by negative 2. When I multiply this equation by negative 2, I'll have 2x here, negative 2x. When I add them together, I get 0x, and therefore I have one equation, y equals some number that I can solve for y. Okay? Now, over here I see the same thing, except that I see this one as 4. If I multiply it by negative 2, I'll have negative 8. Negative 8 plus 8 is again 0, and therefore I'll have y equals some value, and I can solve for y. Okay? But this is the one that happens most often. I don't have a way to do that with the x's, but 12 is a common denominator between 6 and 4. So if I multiply the top one by 2, I get 12x. Multiply the bottom one by negative 3, and I get negative 12x. 12 plus negative 12 is again 0. Right? Now, if I looked, I could have multiplied the bottom number by negative 2 and got rid of the y's. But I just happened to be looking at the x's, and so I dealt with the x's first.
When you have a number that multiplied, do you also have to multiply that number by the...
Everything gets multiplied.
Okay.
Everything gets multiplied. Right, and again, that's all Algebra 1 work. Okay? Now, so when we multiply those, and that's this next part, so when I multiply this one, I end up with these two. I multiply the bottom one by negative 2. What happens when I add the x's together? Get a 0. When I add the y's together, you better say negative 10. Right? And when I add these together, I get positive 10. So I have negative 10y equals positive 10. That means y is negative 1. Because negative 10 times negative 1 equals positive 10. So, and then I bring that back into here, and I can solve for the x. Okay, so the y was negative 1, and the same thing works with that. Now, because somebody's absent today, I don't have my work pencils, so I'm going to have to turn the thing off for a second and we'll get my pencils.